In this example, we're going to be looking at mine haul trucks, and we believe that the amount that each truck carries is described by a normal distribution. And so the mean of that distribution is 97 cubic yards, and the standard deviation is 2.5 cubic yards. And we're asked in part 1, if we select one of those loads at random, what is the probability that it will have a load greater than 100 cubic yards? In 2, we are asked the question in a slightly different way: what fraction of such loads are smaller than 90 cubic yards? And in part 3, we're asked to design the LMAX such that only 1% of loads will be larger than that particular value. So 3 related problems. So we'll start off looking at part 1, and for part 1 we need to calculate our Z associated with 100 cubic yards. And what I always do is remember that I should draw a little sketch, and we know that we have a normal distribution with an average of 97, and we want to know what's the probability that we'll have a load greater than 100 cubic yards. So wherever 100 is, we want to know the probability that it'll be greater than. So we'll have some small fraction of the total number that are greater than 100. To find that fraction, we calculate first the Z. So Z is 100 minus the mean, 97, divided by the standard deviation, and that's 2.5. And so we end up with 3 over 2.5. And when I did that in advance, I got 1.2. So we need to, for that Z, we need to find the corresponding phi of Z. And we can get that from the tables that are at the back of the book, and I have them available here. So brace yourself, there's going to be some changes on the screen. So we need to find the phi of Z at 1.2, and I'm hold on to something because I'm going to zoom. So there we can see for that particular Z of 1.2, the phi of Z is right here, so 0.8849. What that tells us is the probability that it's 1.2 or less, but we wanted the opposite of that. So now I'm going to use that number, 0.8849. Again, hold on to something. Whoops, not that small. We had 0.8849 was this lump, and we want 1 minus that. So we want 1 minus 0.8849, because 1 minus 0.8849 is this portion, and that's what we want. And when I did that in advance, I got 0.1151, or the answer to part 1 is 11.51%. That's the answer to part 1. So we've got that, and in part 2, we're asked to calculate what fraction of loads are smaller than 90 cubic yards. Well, I'll draw my little sketch again. I've got an average of 97. Whoops. An average of 97. And the hump looks like that. And now I'm asked what fraction are smaller than 90. So again, it's some small chunk. And for this case, I calculate a Z equal to 90 minus 97 divided by 2.5 is equal to minus 7 times 2.5, which is giving me a Z of 2.8. So minus 2.8 is my Z. Now I need the phi of that Z. The phi of that Z, you're going to find out, is not possible. We can only get the phi of the minus Z because our table doesn't contain any values for a negative Z, but let's go find that. So in this example, whoops, we need to find the answer for 1.8. And must be on the bottom half. So here's the bottom half. You see up there it says bottom half. So we find it for 1.8. We get 0.9641. So we'll go back to our problem point and use 0.9641. Phi of minus z equals 0. I forgot what that number was. 0.9641. 0.9641. But clearly the 0.9641 is this portion, and we wanted the opposite. We wanted 1 minus that, so we want 1 minus 0.9641, and that's one of the consequences of only having the positive values of the table. We have to always draw these figures to make sure we don't use 1 minus what we need. So our answer is 1 minus 0.9641, and that gives us 0.0359, or the answer here is 3. Ooh. Our answer there is equal to 3.59%. Lastly, part 3 asks, if the dump area is to be designed for those for these loads, what is the size L max that we should select so that only 1% of all loads are larger than this? I'm going to use the next sheet for this. So I want to find the L max such that only we don't know L max, but we want only 1% to be contained in that point. So what we have here is we want the phi of z to be equal to 0.99, because again, phi of z is always the probability that it's that value or less. So we want to find the z that gives us a phi of z of 0.99. So let's go find that. So we're looking in this column here for the 0.990. 0.990. There, oh, we're not quite there. So it's between these two. And in fact, what we want to do is we want to use linear interpolation to get the right value. And if it were any more complicated, you wouldn't be able to do it by inspection, but we can see that the z that we want is equal to 2.3267. 2.3267 is the z we want, so we'll go back to our problem and continue with that. 2.3267. That's the z we want. That z is going to be equal to the L max of interest minus the mean divided by the standard deviation. So 2.3267 is equal to L max minus 97 divided by 2.5. And when we solve for that, we get an L max equal to when I do this, I get 104.1 cubic yards. So that's my answer to part C, and that's case T solved.